So let's go on and talk about the ear, the physiology of the ear. But we can't understand the physiology minus understanding the anatomy of the ear. So the ear has got too many special senses, the vestibular system and the auditory system. Comes to the vestibular system, that's balance. Auditory system, is very important in communication. You can't communicate well socially if you can't hear, because you'll not be able to understand what someone is trying to say, if they're being romantic or if they're being harsh, right? Anyway, about romancy, it can also be out of word. You can as well communicate it in action. But then hearing is also vital when it comes to protection. Imagine you heard a gunshot. What happens? Run, bro, run. So you are going to move from the place. That is a protective mechanism. And when you're talking about the physics of sound, sound is actually a pressure wave. Think of, you get a stone, you throw on the waters. What is going to happen? You are going to create those waves, right? That's same with sound, but it's just that these are pressure waves created by vibrating air molecules and not water molecules. Sound has got properties: waveform, phase, amplitude, frequency. When you're talking about how high or low or the loudness of sound, that is known as a pitch, and it is determined by frequency. What determines the pitch or the highness or lowness of sound? Frequency, which is measured in per second or second to the power negative 1, or hertz. The normal audible frequency range is 20 hertz to 20 kilohertz in a normal human being. In infants, it's about slightly higher than 20 kilohertz. As we get to grow, most of the organs deteriorate. And so what happens is that the highest or the maximum that you can hear is 17 kilohertz. That's why if you're talking to grandpa, you are going to be shouting, they are not getting. Can you say that again? Yes, they've grown. And so the upper limit of the audible frequency has reduced to 17 kilohertz. Sensitivity to sound is also dependent on the speech. For example, bats have got a small auditory sensitivity, so it is dependent on the species. And then the magnitude of sound, how big sound can you hear, is expressed by intensity. There is a minimal sound intensity that you can hear, and the maximum, such that when you hear it, it hits your ear. Because of large difference in sound intensity, we express sound intensity as the logarithm of the ratio of the measured pressure to a reference pressure. Okay, or logarithm of the actual, we get the logarithm of the actual sound intensity. So if this is the actual sound intensity and it is small, of course base can measure it in terms of pressure. You want to express it as a logarithm, that is going to give you now sound intensity is going to be in decibels. So if you just hear decibels, you are going to see logarithm of the actual sound intensity. Now let's discuss more about the ear. Well, to start with, if I can be an artist for a bit, this is the external aspect of it, and then we are going to be going like that, and then we are going to have, let me put it in color, we are going to have another structure here. Okay, we have got this structure there, and then to this structure we have got a nice small structure that is going to attach here. And then to this nice structure we have got another structure that is going to attach to it. And then to that nice structure, we are going to have also another part that is going to attach to it. And then after that, we are now going to have some interesting structure, if you can also see how they look. Okay, we are going to have something like that. Have you ever seen a snail? So we have got that snail-like structure. And then we also have these parts which are going to be going like that. Hope I'm drawing them well. Well, we already said that we are not artists, isn't it? We are medical people. So, and then at the end of these structures, we are going to have bit of dilatations. Not the best drawing you are going to find out there, but at least communicating something. There are also going to be some few dilatations here and there. So this is basically what is at least telling us something about the ear. So the ear is going to have first the external part. So I've got the external ear, and then can you see we have got this part here? Okay, the way I put is not inclusive of that other part. We have got this part here. Let me put it properly on top. I can put it in that color. Okay, we have got these parts. This is known as the middle ear. And then we have got these structures. Basically, this whole thing that you can see like a sh, like a snail, and the other parts. So I can put this here. That's known as the inner ear. When you start with the external ear, what makes up the external ear? We have got the outer part. We have got the pinna. We also have what we call the concha, which will be basically getting sound. And then we have got also the external auditory meatus. This entry going inside there into the middle ear. And then when we go to the middle ear has got this membrane here. What's the name? I can give it A. And then we have got this small bone. I can give it B. We have got this small bone. We can give it C. We have got this bone. We can give it D. So for the middle ear, A, that's known as the tympanic membrane. Tympanic membrane. And then B, the first bone that attaches to the tympanic membrane, that's known as the malleus. Bone that attaches to the malleus, that's known as the incus. And then you have got the last bone that is attaching the incus to the components of the inner ear, that's known as the stapes. So the first component of the middle ear, we have got the tympanic membrane. The second component, we have got bony ossicles. So these are called bony ossicles. And then the third component, because this is number two, number one is this one. The third component we call the muscles. We have got two muscles. So we have got the tensor tympani, even from the way to be able to tense the tympanic membrane. And then we also have the stapedius, which attaches to the stapes. Think of S for second pharyngeal arch. So this one, what is the nerve that innervates the second pharyngeal arch? Is cranial nerve number 7, the facial nerve. And then the tensor tympan comes from the first pharyngeal arch. What's the nerve of the first pharyngeal arch? That's cranial nerve number 5. So a branch of the cranial nerve number 5. So these are the parts. Now, the tensor tympani and the stapedius, these are structures are basically there. Their aim or their role is to be able to contract, and when they contract, they are going to reduce the the destructive effect of loud sounds on the tympanic membrane and the delicate parts that are found in the middle and the inner ear. Right? So when they contract, so what happens is that they are involved in what we call impedance matching. Now, impedance just refers to a medium Z resistance to movement. Remember, so what you need to know is that the external ear and the middle ear, they have got air. They are filled by air molecules. The inner ear has got fluid. And impedance, we are saying it is a medium resistance to movement. So which one do you think is going to resist sound more? Is it the air or the fluid? So air has got low resistance. So there is low impedance in the external and the middle ear. So as sound is traveling from the low impedance medium to the high impedance medium, which is the inner ear, what happens that acoustic energy is going to be lost. Acoustic refers to hearing, right? So energy is lost. So what happens is that the tympanic membrane that you see here is going to increase the energy, is the acoustic energy, and it is going to increase it actually up to 200 times, so that as the sound is traveling from low impedance external and middle ear to the high impedance inner ear, at least the energy, the acoustic energy is not lost, so you can still hear the sound that entered the external and the middle ear. Hope we get that right. So that is going to be the function of the middle ear basically. So what happens is that when sound passes, the function of the external ear is basically to receive sound, to transmit sound, and to localize sound. So for you to understand which side is the sound coming from, is it from the left or from the right? So if sound is coming from the right, it means that sound is going to hit the right ear faster. So that is going to be also the function of the external ear, to be able to tell where sound is localized or where sound is located. When sound passes in the external auditory meatus, this one, it is going to hit the tympanic membrane. The tympanic membrane is going to vibrate. Its vibration is going to cause the vibration of the Marius, and then the Marius vibrating is going to transmit the vibration to the incus. Vibration is also going to be transmitted to the stapes. The stapes is connected to what we call the oval window. The oval window is actually a structure of the cochlea, and then there in the cochlea you have got what we call the basilar membrane. The basilar membrane is going to start vibrating, and the vibration of the basilar membrane is going to cause, now on top of the basilar membrane we have got what we call the air cells. Those guys are going to start moving up and down, up and down, and up and down, and that is going to be now the physiology to talk about. Well, before again to go to the details of that physiology, let's understand again about the inner ear. So the inner ear has got these parts which are going like this. Okay, something like that. So the inner ear is involved in two things. There is a vestibular system and the cochlear part, which is hearing. So this part, which is like a shell, this is known as a cochlea. And then the rest of the parts here, this is the part that is going to be involved in balance. Involved in balance. So the parts that are involved in balance, we are going to have these three parts, this one, and this one. We call these as the semicircular canals. Okay. And then we have got a part here which we call the utricle, and then we have got a part there that we are going to call a circle. The semicircular canals, at the end of them, can you see that there is a dilatation? All of them are going to have a dilatation at the end, and we call it the ampulla. That ampulla has got what we call the crista ampullaris, and that crista ampullaris is going to have air cells. We call them type 1 and type 2 air cells, which are going to be involved. So the semicircular canals are involved in angular acceleration. So if you move your head to the left, to the right, up, down, nodding, so that is a function of the semicircular canals. The utricles and the circules, these makes up what we call the otolith organ. And the otolith organ is involved in linear acceleration. When it comes to the cochlea, so linear acceleration and angular acceleration, that is balance. The cochlea is involved in hearing. So we are starting first with the cochlea, which is involved in hearing. So if we get the cochlea, we make a cross section of it. We are going to see three canals inside of it. We are going to have a canal that is on top, and then a canal that is down. So the canal that is on top in the cochlea, we call this as the scala tympani. Okay, actually the scala vestibuli. And then we are also going to have the scala tympani, and then the middle part, this is known as the scala media. So the first two that I mentioned, the scala vestibuli and the scala tympani, these guys are similar to extracellular fluid, ECF. What is the main ion of ECF? Scala media is similar to ICF. Remember, P's are more inside the cell. What do we mean? Potassium phosphate proteins. So this one is rich in potassium, while the outside of the cell is rich in sodium. Now, when you look at the scala media contains what we call the organ of Corti. So, what does the organ of Corti contain? The organ of Corti is going to have air cells and another important structure. So, three basic parts. You have got the outer air cells, you have got the inner hair cells, and you also have what we call the spiral ganglia. The inner hair cells are the many sensory receptors. Okay, the main sensory receptors of the of sound waves. That is important for us to know. There are many sensory cells. Now, when it comes to the, remember we have said that the inside of the cochlea, you are going to have the basilar membrane. So we are going to have this membrane. This membrane is actually running the entire length. So if the cochlea is like this membrane is going to run the entire length of the cochlea. And this membrane has got cells. And these cells, you have got the inner ear cells and the outer ear cells. The outer ear cells are arranged, the three of them, like that, in three rows. These are the outer. And then you have got one ear. So together, you have got four rows. Okay. On top of these guys, you have got what we call the tectorial membrane. So that is a membrane that is on top of those guys. Another thing that we should be able to understand here is that we have got some supporting cells. Okay, we have got some supporting cells in the organ of Corti. We have got what we call the pillar cells. We also have what we call the pharyngeal cells. So these cells, we have got the outer and the inner cells. The outer pharyngeal cells are also known as the delta cells or data cells. These are the outer pharyngeal cells. Okay, there. At least we have understood what is happening. So now let's go into a bit of detail about what is going to lead to the generation of an action potential and that stimulates the hearing that we can hear. This is the membrane, that's the basilar membrane. We have got this as our cell, our inner ear cell. These cells have got cilia, and the cilia goes from the longest to the shortest like that. The longest cilia is known as a cilia. The shorter ones are known as stereocilia. But then in human, the longest, which is the kinocilia, disappears. So we just remain with the longest stereocilia. And these guys are attached by what we call tip links. These tip links contain potassium gated channels. So what happens is that when an action potential comes from the external ear to the middle ear, it stimulates the vibration of this membrane, tympanic membrane, the medius, the incus, the stapes, and then via the oval window, the vibration is going to spread now to the cochlea, right? And that because the cochlea, the entire length of the cochlea has got the basilar membrane. So the first part of the cochlea, we call it the base, and the end is known as the apex. So the sound is well represented in these regions. The base of the cochlea responds to high frequency sounds to cause the vibration of the high frequency sound to cause the vibration of the base, while the apex responds to low frequency sounds. So what is going to happen is that when the basilar membrane starts to vibrate and the basilar membrane has got the air cells will start vibrating. This is how an action potential will be generated. When the air cells start vibrating, what happens is that the shortest stereocilia is going to move towards the longest stereocilia or the kinocilia. And what happens is that the tip rings which contain the potassium gated channels are going to open. What happens that the potassium now will be able to flow into the cell. And then near the base, the potassium will be able to move out. And then calcium will be able to enter the cell. And when this calcium enters the cell, it is going to lead to exocytosis of glutamate, which is a major neurotransmitter in the central nervous system. This glutamate is now going to go to the postsynaptic cell, and then it will lead to a depolarizing potential. But you have got a lot of these air cells, right? A lot of them, and when they all get to have this depolarizing action potential, they're all going to bring their nerves together like that. And that is going to lead to what we call the spiral ganglia. Remember, ganglia is just a collection of cell bodies in the central nervous system. So that is going to be the spiral ganglia, and that is what is forming the cochlear division of the vestibulocochlear nerve, cranial nerve number 8. And that is going to go to the central nervous system. So basically, that is how an action potential is generated. Remember, if that's for the physiology of hearing, never forget about what is happening with the ions. That is very, very, very important there. So when we have generated this action potential, then now we are going to go to the what? We are going to transmit the impulses. We are going to go to what we call the cochlear nucleus. Okay, because this is hearing, right? We need to go to the hearing center. So the nerve is then going to send fibers. Now I've only these cells which are picking up sensory sensations, the sound waves. These are the inner ear cells. What is the role of the outer ear cells? The outer ear cells receive efferent. They receive information from the brain. Okay, and those efferents are coming from the superior olivary nucleus. And we call this because the information is coming from the superior olivary nucleus going to the outer ear cells. We call this bundle of nerves as the where are we coming from the olivary nucleus. So we call that as the olivo. Where are we going? We're going to the cochlea. Olivo cochlear bundle. So the olivocochlear bundle is the one that is stimulating the outer ear cells. When you stimulate the outer ear cells, then that is going to make, now the information is coming from these guys outer ear cells, stimulating the basilar membrane to vibrate all the more. That is how you modulate auditory impulses, right? So the outer ear cells are involved in modulation of the auditory impulses, not really as taking up the sensations for hearing. Hope we have gotten that. So you can see also these structures the way they are arranged. Okay, so this is going to be the cochlear branch of the vestibulocochlear nerve. You can see the pinna there and the concha and the external auditory meatus. Okay, so the human ears are sensitive to about 2 to 5 kilohertz. This is how much sound that is related to speech. This is the frequency of sound that is related to speech perception. For you to get speech, like just from 2 to 5 kilohertz. The pinna and the concha is basically involved in providing core of sound source. In which direction is the sound coming from? The middle ear, as we said, those are the parts. You can see how they are connected. The medius is attached to the tympanic membrane, the incus, and then the stapes that is attached to the base of the oval window, right? So sometimes they can be paralysis. Remember, I said the stapedius is innervated by cranial nerve number 7, tensor tympani by cranial nerve number 5. And these muscles are just here to be able to respond to loud sounds, protecting the inner ear. So if there's a flaccid paralysis of any one of these muscles, like in Bell's palsy, there is a problem with cranial nerve number 7. And so what happens that you are not innervating the stapedius. So what happens that is going to be painful sensitivity to moderate or low sounds which are supposed to be normal, just like right now the way I'm talking, you are listening to me normal sound, right? But then as you are listening to my talk, you start having pain in your ears. That is known as hyperacusis. So the inner ear, again, we have got the tectorial membrane. Okay, we have got the basilar membrane, membranous labyrinth. Now the inner ear is engulfed in the bone, the petrous part of the temporal bone. So I've gone the inner ear is also known as a labyrinth. So I've gone the bony labyrinth, just that part of the bone that engulfs this inner ear. And then now the structures which are inside these parts, we call it the membranous labyrinth, which is going to now contain the cochlea and these other parts. Inside the cochlea, I've got the basal membrane, the tectorial membrane, organ of Corti. Okay, so again you can see this is the scala vestibuli, the scala tympani down, and then we have got the scala media, which contains endolymph with the hair cells. And you can see this is the stapes that attaches just somewhere. We've got the oval window. We also have the round window that is opening in the scala tympani there, right? You can see inside the cochlea we have got a duct. This duct we call it the cochlear duct. Actually, it's also known as the scala media. Okay. You can as well see the cells again. The outer ear cells arranged in a row of 3. Inner ear cells is just one. On top we have got the tectorial membrane. Down we have got the basilar membrane. These are all going to come and merge to form the spiral ganglia that is going to take the information. Okay. So you can see that the inner hair cells, their artery resting membrane potential of negative 45, while the endolymph, you can see the endolymph, you have got positive 80 millivolts. There is high potassium, so the resting membrane potential is positive. You can as well see the outer ear cells arranged in a row of 3, inner ear cells just a row of 1. That's the organ of Corti. Now, inside the hair cells, the membrane, rest membrane potential is negative 45. That's inside. And then the perilymph, that is outside. The membrane, the endolymph first. Okay, so this is our inner air cell or outer air cell. Endolymph has got a potential of positive 80 millivolts relative to the perilymph. And then inside the hair cells, we have got negative 45. So if you take a difference of this, negative 45 minus 80, that will give you 125. What does that mean? It means that perilymph inside, it is negative, it is 125 times more negative than the endolymph. Remember, endolymph is here where I've got positive 80. So inside hair cell, we have got a resting membrane potential of negative 45 than perilymph, and 125 millivolts more negative than endolymph. Now, where do we find endolymph and where do we find the okay, endolymph is basically here, and then here you have got what? You are having the perilymph. Please take note of that number. Can you see that inside the air cells we have got negative 45? But inside the scalar media, that's the endolymph, you have got positive 80. So the inside is 125 times more negative. Take note of that number. We've already talked about the mechanism of sound transduction. We also know how it happens. So what happens is this. When the shortest stereocylia moves towards the longest stereocylia, there is action potential being generated. But if the longest stereocylia moves towards the shortest stereocylia, there's going to be closure of these potassium channels. And so what happens? The inside, you don't have any positive charge going inside. So there's going to be just negative charge inside. And that leads to hyperpolarization. And so meaning that no action potential is going to be generated. Okay. Sometimes someone can have a problem that is known as tinnitus. That is you basically hearing ringing sensations in the ear. That's tinnitus. So you can see when we get to when sound waves are generated, or the action potential generated from the cochlea, where is it going? It is going to the ventrocochlear nucleus and the dorsocochlear nucleus. But then understand where the waves are going from here. From the ventrocochlear nucleus, we are going both to the contralateral and ipsilateral superior olivary complex. Superior olivary complex. Please take note of that. All right. So when we go, remember we're coming from the what? From the ventrocochlear nucleus. And that is going to form. So the nerves that are going, or the bundle that is moving from the ventrocochlear nucleus to the superior olivary complex on the contralateral aspect, that forms what we call the ventroacoustic stria, also known as a trapezoid body. Please take note of that. And then from the dorsocochlear nucleus, we are having impulses. One, going from the dorsocochlear nucleus, you can see they are going to the contralateral side and then going to synapse in the inferior colliculus. And this is found in the midbrain, inferior colliculus. And that is forming, you can see this tract, we call this as a dorsoacoustic stria. But then another bundle, you are having some nerves or some bundles coming both from the ventrocochlear nucleus and the dorsocochlear nucleus, going to the contralateral side, also in the inferior colliculus, and that is forming this bundle also. Okay, you can see this bundle here, which we are also, this one we are calling it as the intermediate acoustic stria. Please, you need to understand this. Let me try to write it slow now. So remember, let's say this is the ventral cochlear nucleus. This is the dorsal cochlear nucleus. So what is happening? From the ventrocochlear nucleus, we can have fibers going both to the contralateral side and the ipsilateral side. Where are we going? We are going in the superior olivary complex nucleus. There's superior olivary complex, and that's in the pons. All right, superior olivary complex in the pons. And this pathway is forming what we are calling the ventral acoustic stria. Ventral acoustic stria is also known as the trapezoid body. Take note of that. But besides that, we can have another pathway. So the ventral acoustic stria is coming from the ventral cochlear nucleus to the superior olivary complex. We can have another pathway that is coming either from, okay, let's first go to the dorsal cochlear nucleus. From the dorsal cochlear nucleus, we are going to have fibers that are going to the contralateral side, but not in the pons, not in the pons, because these nuclei are actually found in the medulla, the rostromedulla. We are going all the way to the midbrain, and in the midbrain, we are going to the inferior colliculus. And this bundle that we are forming, we are calling it as the dorsal acoustic stria. Dorsal acoustic stria is coming from the dorsal cochlear nucleus to the inferior colliculus, while the ventral, which is also known as the trapezoid body, is coming from the ventral to the superior olivary complex. But we can also have some other bundles. Those other bundles, they are coming from both the dorsal cochlear nucleus and the ventrocochlear nucleus. Look at how they are moving. They are also going contralateral, and they are also going to the inferior colliculus. They are coming from both, and this forms what we call the intermediate acoustic stria. Now, can you see that the ventroacoustic stria only ended where? Only ended in the superior olivary complex. You can have actually other fibers synapsing from the superior olivary complex. From here, some other fibers are going to synapse here, and then they are going to go up also in the inferior olivary complex. But these are ipsilateral. Same way here, going up. But then the thing is that from the ventroacoustic stria, you can have also some other fibers that are synapsing going to the contralateral side. So some will go to the contralateral side like that. When they go to the inferior colliculus, from there they are also going to synapse going to the auditory cortex. That's where they are going to be able to terminate in the auditory cortex. That is, you can see where they are ending there. But of course, some of the fibers, before they can reach to the inferior colliculus, they can also end on the nucleus of lateral reminiscus in the the junction between the pons and the midbrain there. The nucleus of the lateral reminiscus. Please take note of how these fibers are moving in that way. That is vital for us to understand. So, what are the fibers going to the superior olivary complex going to do there? The superior olivary complex basically in the midpons. So, information from both interact is a site for initial processing of cues that allow for sound localization. So, superior olivary complex sound localization. Where is sound coming from? All right. And then from the inferior colliculus, those which are going to the inferior colliculus, the auditory information now is interacting with the motor system, is going to relay information to the thalamus and then to the cortex. And this is to do with the aspect of speech and sound harmony. because we're also going to have fibers that are going to project to the Broca's area for speech and then to the Wernicke's area to be able to understand written and spoken language. Okay, hope we get what is happening. So some fibers we've said they'll go to the Broca's area, that is 41 and 42. And then you are having fibers, of course, going to the primary auditory cortex that is located in the superior temporal gyrus. Superior temporal gyrus. And also they are going to terminate to the secondary auditory cortex. And the information there is tonotopically organized, meaning that the high frequency is going to be going to the specific area, low frequency also be going to a specific area. As you can see here, you can see lowest frequency is here on the anterior aspect, the highest frequency is on the posterior aspect. And remember, the highest frequency was corresponding to the base of the cochlea, as we said earlier. Information also go to the Wernicke's area for understanding secondary auditory cortex, right? And also the primary auditory cortex, I mean. Some hearing disorders, you have got otitis media. This is basically inflammation of the middle ear. So, because of some infection. And then there's also hearing loss due to age. That's known as the presbycusis. All right. And then sometimes if there is a lesion to the auditory pathway, then someone will not be able to hear, whether there is a lesion in the central pathway or the peripheral. So, for example, there can be cochlear nerve fibers. There's a lesions. Okay, that's acoustic neurinoma, tumor of the Schwann cells of the eighth cranial nerve. So, if there is that tumor of the Schwann cells of the eighth cranial nerve, that leads to acoustic neurinoma, and so you can't hear well, right? Tinnitus is it's a problem where you start hearing some ringing noise in the ear but not understood about the pathophysiology, but it is basically to do with damage to the cochlea and the vestibular end organs. Some drugs like salicylates can induce tinnitus. Salicylates include drugs that have got salicylic acid like aspirin, bismuth subsalicylate, which is involved in diarrhea. You can use for diarrhea, heartburns, magnesium silate, which is involved to treat pain. Aspirin is also used for pain. So these drugs can cause this tingling sensation, like this ringing sensation in the ear. Deafness can either be conductive or sensory motor. Conductive means that there's a problem for sound to travel from the external ear to reach to this part, the internal ear. So there's a problem in conduction. Okay, so the problem is in the outer and the middle ear. Sensory motor has to do with now from the inner ear that is involved in the getting of sound to all the way to the nerves themselves that are taking the sound, and also to the brain where you are taking the sound. If there's a lesion at any one point there, that will lead to the sensory motor deafness. So they can be unilateral or bilateral deafness. Unilateral deafness, more peripheral auditory structures up to cochlear nuclei, a more central lesion may interfere with localization or discrimination of tone. Bilateral deafness, ability to localize and understand speech could be reduced if lesion in auditory cortex. So if the problem is in the cortex, like the cortex itself, then you can't hear. Because if the lesion is somewhere below, can you see? Let's say the lesion was somewhere here, can you see that there's a lot of anastomosis, or there's a lot of fibers going to the other side, also the other side, fibers coming from the left, also anastomosing to the right? So meaning that if there is a lesion here, I can still hear because of the synapse coming from the other nerves from the other side. But let's say there's a lesion here, it means that already I can't hear. Why? Because there's a lesion here and there's a lesion here. All the fibers that were coming to synapse, taking the information to the auditory cortex, are not working. So that is what is going to lead to failure to hear. That is going to be bilateral. So in testing hearing problems, you can use the Rhines test and the Weber's test. Weber's test is you basically getting a tuning fork, you're putting on the forehead. So what is going to happen is this. In the Weber's test, the hearing loss, if you get a tuning fork that is vibrating, you put it on the middle, and then you can hear the sound equally in both ears. That is normal. But then if you have got, let's start first with the Ryan's test. Ryan's test, what you do is that you get a tuning fork, you hit it on a hard surface, maybe your bony prominence. You put it first on the mastoid process. If you stop hearing the sound, you bring it near the ear. You should still be hearing the vibration when you bring it near the ear. That is normal. That is telling you that hair conduction is supposed to be greater than bony conduction. So sound should still travel in the hair. You should still hear the sound than when you put it on the bone. But then let's start with conductive loss of hearing. In conductive loss of hearing, what is going to happen is that when you get this tuning fork, you put it on the bone, you'll be hearing the sound. But if you put it on the ear, you'll not be hearing the sound. Why? Because there's a blockade in the ear. That is why it is conductive. There's a blockade in the ear. But then if you put it on the bone, the sound can still be picked by the inner ear. But if you want the sound to be picked up by the external ear and the middle ear, it will not be picked up. Why? Because there's a blockade. So there is a bony conduction being greater than the air conduction. And when you're using the Weber's test, what you are going to hear is sound is going to be localized on the affected side. So if this is the side that has got a problem, you are using the Weber's test, you are going to hear sound high in this ear. For sensory motor, the problem is not with the outer ear or the inner ear. So when you put the tuning fork here, okay, you will still be able to hear normally, like the air conduction is still going to be normal, greater than the bony conduction. So when it comes to the Weber's test, the problem is going to be with the other ear. Let's say, for example, you found out that this ear has got a sensory motor problem. For the sensory motor problem, the Ryan's test is going to be normal. Okay, it's going to be normal. But the Weber's test, what you are going to see is that the problem is not going to be here. You are going to be getting the problem here, not be able to get the sound well here. Hope you've gotten that. So basically, that is that. And that is what we're going to end with the auditory system. The next, we'll talk about the vestibular system and example.